My name is Hedley Appley, and in this session we'll take a PTC's model-based systems engineering solution. I'll start out by looking at some of the challenges of systems engineering, and then look at PTC's MBSE solution in more detail, including model-based systems engineering, asset-based modular design, and system product lines. We'll then look at how we integrate systems engineering into your lifecycle and with your existing tool chain, look at the systems engineering process and its governance, and finish off with some examples of model-based systems engineering in action. So let's start by taking a look at general systems engineering challenges. We're all seeing a broad impact of physical and digital convergence. Smarter products, connected products, even smart cities, smart farms, and smart manufacturing. One example is the automotive industry, where cars used to be purely electrical and mechanical, and then were extended with software, with new user interfaces, sensors, electronic controls becoming smart products. And now the connectivity of those smart cars, so they can communicate not only with GPS and control centers, but also with each other for autonomy. This is really an evolution into products being part of a larger system, and this means that we need multidisciplinary product development to cover all those different domains. So let's take a deeper look at some of the challenges of systems engineering for smart connected products and systems. Firstly, we're seeing a significant growth in the complexity and functionality of the systems and their software. In fact, a much larger share of the product cost is now software. We're also seeing systems being built of subsystems, so in a modular way, plugging subsystems together to build larger systems, either provided by one organization or by partners, or even by disconnected organizations. Certification and regulation are also becoming more important, particularly in industries such as aerospace, automotive, rail, energy, etc. The second main thing that we're seeing is larger and more distributed and multidisciplinary teams with barriers to communication and collaboration. So they need a common place to work together and share their goals and get stakeholder buy-in. And as well as those focused systems engineering challenges, we're always seeing the same challenges of delivery on time, to quality, and reducing cost. And particularly with systems engineering, we need to see in most cases requirements traceability and impact analysis, so that we can make the decisions about where the functionality should be best located. And then in systems engineering specifically, we're seeing some new trends. So we're seeing more rapidly changing requirements and shorter iterations of delivery. We're seeing models as the core of communication between all stakeholders. Incremental functional analysis, executable requirements with SysML, architecture to enable parallel teams to work on separate subsystems, and also the need for asset-based modular design of subsystems and their interfaces and system variability. As you can see in this chart, people are moving from having no standards to being standards compliant, activity-based to goal-based, no integrated engineering to systems engineering, as well as waterfall or V-model processes, applying some agile and incremental approaches. Moving from small co-located teams to large globally distributed teams, and particularly moving from document-based using Excel, Word, textual requirements to model-based systems engineering. And model-based systems engineering is now recognized as the most agile approach to systems engineering. And the time is now. These recent papers from PTC on how smart connected products are transforming competition and companies, from Michael Porter and our CEO Jim Heppelman, pull out some important points. So smart connected products require functional rethinking of the design, and at the most basic level, product development shifts from largely mechanical engineering to true interdisciplinary systems engineering. This means you need a focus on systems and not just discrete products. It also means you need to consider systems of systems. As products become components of broader systems, the opportunities for design optimization multiply. So now that we've taken a look at the challenges in systems engineering, let's take a look at PTC's model-based systems engineering solution. PTC provides a collaborative model-based systems engineering solution to give a holistic, multidisciplinary and collaborative approach to designing and maintaining complex systems. Where this fits in the whole system lifecycle and product engineering lifecycle is a general thin slice across the top, where the product will then be separated out and built as parts of software, maybe using electrical engineering, mechanical engineering, hydraulics, etc. And requirements engineering is really a subset of the whole model-based systems engineering. With our solution, you may also flow down into designing software, so we have that flow down, and we also consider the engineering processes you use both during systems engineering and as you flow down into product design. So let's take a look at model-based systems engineering first. The core to MBSE is the unification of all of our multiple domains of engineering. Firstly, we provide a common language, and this is an industry standard language, which is the OMG SysML, Systems Modeling Language. It provides functional modeling, structural modeling, well-known things like use cases, incremental modeling, and modular design, allowing simulation and trade studies. Having this common language, and in fact this common tool and common database, allows all of your stakeholders to agree and understand the design. It provides whole team transparency and access to the system of record for your systems architecture and system design. It really keeps all your stakeholders in the loop using a common language. Then on top of that underlying shared system design, we can validate the complex behavior much earlier in the life cycle using visual simulation of our system functionality. Again, we can share this with our stakeholders to get buy-in, and we can record the simulation results for analysis. As well as simulating the model, we can also then co-simulate with third-party simulators such as MATLAB Simulink. This gives us very early visibility of our system functionality before we prototyped any hardware or any software. And if we can find problems here, then they're much cheaper to fix than later in the systems engineering and product engineering lifecycle. We also need to provide safeguards in our design and design quality in rather than trying to test it in later in the lifecycle. So along with the standards language compliance and ensuring that engineers apply SysML correctly, we also need to provide and do provide traceability from requirements through to our functional designs, into our structural modeling, and indeed even into our variability designs for product lines. This allows us to find the impact of change. So if we change a requirement or change some system parts, we can assess the impact and check that we're building the right system and building the system right. We also provide quality assurance of our design with management dashboards of completeness and correctness. And along with a reuse platform in Integrity Asset Library, we can reuse quality modules in our designs over time. And then drilling down a little deeper into how we organize our models, as well as following a well-structured V model, we can also add on incremental modeling to support agile approaches, allowing us to identify increments of system design and delivery, and then allocate functions and architectural structural parts of our system and design to be developed against those increments, giving us an additive and evolutionary modeling approach. We can also then just deliver enough modeling to deliver our systems and our products. So that's the basis of PTC's model-based systems engineering solution. Now let's look at asset-based modular design. SysML is great for modeling systems, But once they become very large and complex systems, then the models also become very complex and very large, which kind of defeats the object of having a model and abstracting and being able to see the wood for the trees. So what we provide is a solution to this challenge of having very large models with challenges around access control, configuration management, distributed teams working on different parts of the system. And our solution is to provide asset-based modular design, providing an asset library that then connects models to separate models of the subsystems. So you can build systems in an architectural system of systems approach. This gives you real agility, so you can use a palette of parts at system design time for a real architected modular approach. The component interfaces are also defined and managed in the asset library, and this allows you to build a supply chain for systems engineering with parallel working and delivery of separate parts into a central asset library, maybe based on core requirements at the architecture level, and then use of those assets in various systems over time. We've used standards for the asset library, so we use the OMG reusable asset specification for the meta model and the OSLC asset specification for access to those assets. This is a unique approach to asset-based modular design of systems. Now let's take a look at then layering on system product line engineering. So just as we saw challenges with the growth of systems complexity, we're also seeing challenges around system product lines. How to decide between various options. Customizing existing capabilities to suit new client requirements, and redeploying common systems and software to the market. Our solution to these challenges is model-based product line engineering. This helps you make better trade-off decisions and really gives you agile system product lines. What we do is provide variability modeling in parallel with model-based systems engineering. So just as asset-based modular design was an add-on approach for the core of MBSE, this model-based product line engineering approach is also an add-on to the core of MBSE. We can extend our MBSE models to be 150% models to represent system product lines or system families. So we have many different options which wouldn't be delivered in one single system. And then in parallel, we can model the variability using variability modeling with variation points and variance. This is truly orthogonal to the underlying system model and can be in the language of the customer or the marketing department, so that you can understand the choices that are available. Once you've modeled both the base system model, system family model, and the variability model, then you can make choices and selections on those variants for a particular product instance or a product model, which you can then run trade study analysis on using budget reporting or simulation. And this is a really rapid approach and clean approach to making models of families variable and then deciding which are the best options for a particular customer or a particular market. To look a little deeper, here's an example of variability modeling. Not only does it have inclusion, so here we can see we have various truck types, city type, a truck and a long haul, and the choice of those variants gives you different cabs that are included, the day cab and sleeper cab. But our variability modeling also includes parameterized variability, so things like sizes and lengths, colors maybe even of different parts of our system, and multiplicity, so the number of those parts, so in this case the number of axles. So a very simple modeling approach, but very powerful. And behind this we also have full algorithms, so you can make very complex variability decisions. And again, this is unique to PTC, variability modeling integrated with model-based systems engineering for system product lines. So now let's take a look at lifecycle integration. As we saw earlier in this presentation, the systems models are becoming the main platform that's shared between all the stakeholders and different engineering domains. So we need to then connect up to those tools that are used by other engineers. One example is our connection with PTC's Windchill PDM link, with two focuses, productivity gains and traceability. So let's take a look at productivity first. The benefits that we can provide are to take existing system models and system architecture and use them as a first cut bill of material or part structure in PDM link. This saves time by reusing that existing design information and also improves quality rather than retyping part names from our system model. And as we're doing that, we're also creating automatically trace links between the system model and the bill of materials. We can also add trace links independently between existing part structures and existing system models, and those trace links are very useful for impact analysis, particularly around change, maybe from changing requirements that then change the system design, or either changing in parts or new parts becoming available that you may want to use in future system designs. It also helps you prove that you're actually building and implementing the right system and building the system right. This gives us full lifecycle traceability, all the way from requirements through our system models and their functional model, their structure model, maybe even the variability model, through to PLM into the bill of materials with its part structures, options and variants, and full bidirectional traceability across that whole system model, and it links out to the toolchain. As well as toolchain integration, there's lots of other opportunities for productivity and quality improvement. Another example is our integration with PTC's ThingWorx technology, our IoT stack. We're able to design systems of systems and IoT systems in the MBSE solution. So we can design mashups, system context, how systems interact with people and other systems, the connectivity, and also design the devices and the code that runs on the devices in our system of systems. So that's the PTC Integrity Modeler design environment, which is multi-tier and allows system of system design. And we saw earlier asset-based modular design and system families. Once we've done that design, we can then use that information to do things like automatically generate documentation or automatically generate code for our system. In this case, we can generate device code for ThingWorx, connectivity code, and everything you need behind the scenes to create mashups, dashboards, and control applications. So that's generating automatically ThingWorx ready code at the press of a button. As well as generating code, because we have the system model and we can simulate the system model with the system simulator, we can also simulate and pass the information from the simulator up to the cloud and up to ThingWorx. And in this example, we can simulate with ThingWorx in the loop, showing the mashup running as if it was running onto real devices, but receiving information from our system model and the simulation. This lets us test the mashups very early before we've created prototype software, prototype devices, and also improve our system design and ultimately our system and our product by very early validation of our functionality. We can also feed real data from ThingWorx edge devices into the simulation to help validate that our design was correct in the first place, and also improve our design, our simulation, and ultimately our product. So those are a couple of examples of integration into the toolchain. There are many more. We integrate with other products like Doors, MATLAB Simulink, and others. That really gives you the connectivity you need across an integrated toolchain. As well as that integration, we also need to consider process and the governance of the processes for systems engineering. As well as the tools and techniques to use during model-based systems engineering, we also need to consider the process of systems engineering and how we govern that process. In PTC's MBSE solution, we provide out-of-the-box documentation for industry standard systems and software engineering processes. We provide these in a tool which give you core processes which you can then enhance with your own best practices based on your real-life projects. We provide updates to those processes over time, and you can then use the tool to configure the process, tune the process in a modular way with editing and authoring. The tool provides automatic process diagramming using a web-based multi-device user interface. You can use it to run projects and gather metrics for improvement of the process in the future. And it also has a very powerful process tailoring wizard to give you truly agile processes based on answering simple questions about your product or your system and generating project workflows for that project. The core process that we provide is the PTC Integrity Process Perspective. It's a model-based systems engineering process based on industry standards like ISO 15288. It has three main parts which match to the things we've already talked about in the presentation. A process for model-based systems engineering, an add-on optional process for asset-based modular design, and an add-on optional process for model-based product line engineering. It consists of approximately 311 techniques with 200 tasks, identifies 22 resources and 50 products. That said, you can then use this as a framework and extend it, configure it to match your own best practices. So it's a starting point. It saves you lots of time researching different model-based systems engineering approaches, but then you can use it as a starting point to carry on and tune and improve and create your own best practices for model-based systems engineering. But at the core, it's our recommendation for using PTC's model-based systems engineering solution. Many customers use both that process and approach along with the whole PTC model-based systems engineering solution. So let's take a look at a few examples. Firstly, Alstom Transport, who build train systems, rail and rolling stock. They use the whole suite of PTC's MBSE solution. They use model-based systems engineering, they're moving into asset-based modular design, and they're already making great use of model-based product line engineering for their product families and variation. They found that our modeling technology significantly improves quality and consistency and reduces effort throughout the whole design lifecycle. Next, we have Chira, who build air and space flying test labs. With PTC Integrity Modeler and PTC's model-based systems engineering solution, they've dramatically improved the quality of the work while reducing the time taken to keep their artifacts consistent throughout the design lifecycle. Another example is PSA Peugeot Citroën, who use the MBSE solution and PTC Integrity Modeler as their tool of choice for their global infotainment system. Integrity Modeler significantly improves the quality of the global infotainment system engineering process at PSA Peugeot Citroën, reducing the project design time and development costs. And then finally, Safran from Snecma, who build jet engines and rocket engines. They have the challenge of not having a model-based systems engineering process or tools. And while they started with some best practices in simple documents, they really wanted an approach to document that more widely and improve it over time. So they used PTC's MBSE solution with the starting point of our MBSE process to enhance that process and deploy it across all their systems engineers. So those are 4 very simple examples of PTC's MBSE solution in action. So just to summarize what we've seen, PTC's MBSE solution can help you dramatically improve the design and validation of complex systems. It responds to the current trends in the market, but also is based on best practices. It helps you with multidiscipline collaboration. The solution runs live on a scalable multi-user database. It integrates with other tools in your toolchain, such as Integrity, Lifecycle Manager and Windchill. It's standards-based for that common language of communication for your systems design. It supports things like SysML and also other standards based around model-based systems engineering and variability modeling. It also provides system-level simulation so that you can visually simulate your system's functionality with the model in the loop, and then optionally extend to have other things in the loop such as ThingWorx and the Internet of Things. As well as that simulation, we can then automatically generate artifacts from the system models. We can generate documentation, but also automate the generation of code to C++, Java, etc., and also our own technology, ThingWorx. It also includes new and groundbreaking asset-based modular design for breaking models up into systems of systems and linking them with an asset library. It provides unique and groundbreaking variability modeling with a parallel and orthogonal variability model that you can link to your underlying systems family model to give you the ability to configure products in a visual way and run real trade study analysis on the various options. And it also provides a very agile, incremental, modular and minimal approach to modeling, so you do just enough modeling to get the system designed and get the product delivered. These set of unique features of PTC's MBSE solution make it invaluable to our customers, and I'm sure invaluable to you.